These are AI-controlled bots designed to play Counter-Strike. But they're unlike any other bots that you will have encountered. They move against walls and other geometry to block enemy line of sight. They push up when defending a bomb to stop it from being defused. They establish and apply pressure on known choke points. They even know how to flank enemies such that they can attack in a coordinated fashion. Their secret is they're trained to develop intelligent coordinated movement, and they do that by using the same AI technology that powers large language models. In 2025, the conversation around generative AI in the video games industry is about the impact it can bring in various aspects of production. Many studios are exploring whether production costs can be minimized through use of image generators and large language models, with much debate around the impact this has on game developers' livelihoods, the quality of the finished product, and the appetite from consumers for games that use AI-generated content. But outside of conversational non-player characters, we're not seeing many examples of what this technology can do that brings value to players, and that's where this project comes in. I'm Tommy Thompson, this is AI in Games, and for this episode we dig into the MLMove project, a concept that shows not only you can use generative AI to improve the experience for players, but you can do it in a way that is completely antithetical to the trends currently running in generative AI. We're going to dig into the research to find out more about how it works. Plus, I sat down with the project's creator, Dr. David Durst, to find out about his experiences in building it, what his ambitions were in creating the MLMove bots, and what potential this has to be adopted in commercial games moving forward. MLMove is an AI bot designed to play Counter-Strike by learning against professional human play. While it's comprised of a number of systems, with the actual combat handled by a traditional behavior tree, the focus, as the name implies, was on building the movement component of the bot, with the position and orientation of all characters on a given team controlled by a generative AI model. Published at the 2024 Symposium on Computer Animation from a thesis supervised by Pat Hanrahan and Kayvon Fatahalian, MLMove was the final project of David Durst's PhD, which he read at Stanford from 2017 to 2024. I had the pleasure of meeting David for the first time at GDC, but a couple of years ago, where he was telling me about his research, and we've kept in touch since. And with the project complete and the doctorate in the bag, I was keen to find out more about how this project had come about and why Counter-Strike was the game to try it out in.
So my PhD was a little bit of a winding process, and I had come in as a database person, done a rotation with some database professors and really enjoyed that. And then I pivoted to doing programming languages for computer architecture, because it seemed like a very interesting field where you could have a lot of impact. And I had this really great paper where I published some really cool results on type theory for designing computer chips. And I realized through that a lot of the great progress was actually going to be made on the application side. That like, hey, you could build these fundamental chips, but if a lot of 10,000x, order of magnitude changes come from building an application specific solution rather than a general purpose chip. It's hard to beat NVIDIA. You don't want to be in the business of competing with NVIDIA. Yeah. And so I was looking around for applications and data sets where I could really be the expert and could both be the technical person and the expert.
Did you go looking for it because you're a CS fan originally? Like, what was the relationship there, I guess?
My advisor's first suggestion was basketball. They have some, like the Warriors, there's some groups that are fairly analytics heavy. I spent a lot of time looking at basketball. Yeah. And there was this problem of the data's really hard when you have to deal with perception. We wanted to get perception out of the loop and deal with the situation where you could just read the state. Because like in a video game, it just seems odd to use a camera to perceive things when the engine knows what's going on. And there are a lot of great AI groups doing perception work. And, so lo and behold, you find HLTV, you find all these great demos. There's a wonderful community of people who have demo parsers. There's demo, I forget the name, it's Demo Lang. There's the Golang demo parser. You should look them up. They're a wonderful community of people. And it's like, great, okay, so we have this amazing data source of human-like behavior. What can we do with it? And so I spent a lot of time trying to find cheaters, because as a gamer, that's the first thing you want to do is like find the cheaters, right? Or like find the network bugs. These are all the issues. But the problem is that like finding cheaters is very, very difficult. The distribution of it's sort of a problem of finding the cheater distribution, sort of finding the outliers. And I did this analysis where I looked at reaction times. And if you define reaction time as time from any visible until time when crosshairs on them, and this is pre-publication, but very dirty data. I sort of measured my friends with cheats on in Counter-Strike, where they have a mode on where you can see the wireframes, not actual cheats, but they have a mode on where you can turn on wireframes and you can sort of pretend to cheat. And you compare that to pros, you see that pros actually look like they're cheating. And these are like in tournament because they're clean, they're legit. But because they've played so often, they're predictively aiming where people will be, and their crosshairs are actually on the enemy like 100 milliseconds before they're visible, sort of like a cheating amateur looks. And so it's very hard to detect these subtle things. And so I realized, and this is sort of winding, but I'll get back on track, is that the real key is that if you want to understand these complex human behaviors, you first need a model of human behavior. And then you can use this model to do really interesting things. This was the hallucinations work I presented with Activision at GDC. That requires a model of human-like behavior, and you can then build these really cool bots to play with for training and testing and all these other cool features. And so that's where it led to, okay, I need a way to model human behavior. And then once we have that model, the world of possibilities open up. And this is where our sort of order of magnitude improvement comes from.
It's worth taking a moment to highlight what this is doing that's different from traditional game AI. Typically, we rely on navigation meshes to move characters around in a 3D environment, a point we've discussed in both the AI 101 episode on the topic, but also we've dug into specific challenges faced in games when handling navigation in complex environments, such as Sea of Thieves, Horizon Zero Dawn, and Death Stranding. However, while navigation meshes are complex and intricate systems, they're not built to support this level of spatial awareness out of the box. You would need a lot of tagging in the gameplay space, and a custom navigation and path-following system set up to have characters move around like this. Plus, hugging the edges of the navigable space and pushing right up on cover can often be difficult for an NPC, given we typically don't bake the nav mesh to be exactly the same shape as the geometry, but rather carve a shape that is going to be useful for gameplay. So MLMove is trying a different approach by training a model that simply learns how to move in the map based purely on how humans themselves move within it. And it's achieved using what is known as a transformer, which we typically use for large language models. One of the most interesting things about MLMove is it takes an inherent trait of how transformers work that is both why large language models have proven to be quite powerful, but equally is the reason they can often be quite frustrating. To summarize, transformers are the neural network architecture that learns contextual relationships within the data that it's trained on, such that it can take an input and generate an output that is likely given their contextual relationship. We typically think of transformers as language models such as GPT, Gemini, and Claude, which learn relationships between words in their training data such that you can ask it a question in human language and it can generate an answer. Notably, it doesn't learn the meaning of the text, but rather how words and concepts relate to one another, and as such can generate answers that quite often make sense until they come under further scrutiny. This is why LLMs are prone to inconsistencies in simply making stuff up, what is typically referred to as hallucinating, because the LLM is simply predicting the next word it should write based on the input, the current state of the output, and what it learned from the training data. It doesn't understand what you asked, nor does it understand the answer it gave, it just predicts a sensible response. While this is frustrating with language models, this is actually a useful feature for MLMove, given it can pretend to move a team of NPCs around in a way that's reflective of how a human team of players might operate even if it isn't 100% accurate. To quote the MLMove research paper, in an FPS game, human players not only have a complex action space, but also demonstrate complex inter-player interaction and coordination that are quite challenging to model in a rule-based system. However, recent work in transformer models show how to imitate the effect of complex human decisions and interactions without modeling the intermediate steps, or decisions, that led to the final actions. So by modeling the data of human players, it gets to the end result of their behavior, having observed thousands of instances, and while it doesn't understand why human players make that decision, it does give us an end product that is nonetheless quite convincing. This is largely because the problem is very tightly scoped.
So the first version of the bot I built was purely running off the nav mesh. You can parse out the Dust2 nav mesh and you can run on it. And I put that on Reddit and people loved it. But the problem was, in order to get it to be really human-like, I had to hand annotate where to stand. Because people don't just follow nav mesh. Pros, like expert players, stand in very specific places that have developed in over decades. They form, they find ambush locations. They know the exact corner and the right person on the corner to do it. And there have been other people who have built bots for Counter-Strike that do similar things. And they sort of always, you take the nav mesh, and the nav mesh gets you to, like 10%, and then like hand-labeled points get you to like 50%. But then you have two remaining problems. A, how do you transition between those hand-labeled points? You have this now complex finite state machine. When do you transition between them? And B, when you're transitioning between them, how do you stand relative to your teammates? Like, you can build one bot that just goes from one to the other, but like, I'm holding a forward aggressive point. When do I rotate back to the site to help my teammates? And when I do that, how close do I stand to them? Because the closeness to teammates depends on factors like map geometry. And then also how much you sort of jitter around in a human-like way to be unpredictable. Because like in Counter-Strike, movement impacts accuracy, and you always want to sort of shoot at the apex of your movement, so your velocity is 0 and your accuracy is maximized. But humans aren't perfect. So how do you sort of model that process of like, managing velocity and hardness to hit and accuracy? And so what we came up, this work we came up with was, let's just think of predicting the next keyboard state. Humans roughly move at about 100 milliseconds to 200 milliseconds. There's some great literature on that I can send you. And you can sort of think of the brain as sort of a pipeline processor that takes in, it processes 100 milliseconds and then acts on 100 milliseconds. And so you can think of it as sort of like 100 millisecond chunk processes. And so we can think of this as, hey, just predict what the keyboard state will be over the next 100 milliseconds.
As Durst explains, this transformer model, a language model of movement, if you will, is being trained solely to run on Dust 2, and he specializes the model to only work on Dust 2. While your first instinct may be to build the model to handle all maps in Counter-Strike, in this case, it actually makes sense to specialize the model to a single map, given professional players learn multiplayer games by repeatedly experimenting with strategies to fit a specific level. As such, he's training an AI model that reflects human behavior. In order for MLMove to be trained, you of course need some data. This led to the creation of the CSKnow Dataset. While there are existing datasets on Counter-Strike for learning the game, they're not necessarily focused on learning the movement of each player. To that end, Durst curated a dataset of around 1100 hours of play on Dust 2, and then reduced it down to 123 hours, with a focus on 17,000 rounds of retakes, the custom mode where 4 offensive players have 40 seconds to retake and defuse a bomb site, with 3 opposing players defending it.
Like, what was that process like in kind of curating that data and getting it ready for what you needed?
So we initially put on actually like more than that. It was like, I forget the exact numbers. I think this was like 2,000 hours. It was like 1,000 or 2,000 hours. This is like, those are rough numbers of data, only on Dust 2. Trying to be very nice, not annoy anyone. Just pull down 1,000 or 2,000 hours and try to be super clean about it. And then when I was looking at it, there's a lot of noise in there. Like warm up rounds, bathroom breaks. Like guys running around with their knife out, just sort of like knifing the wall because they're pros. They have 50,000 hours. Like it's a random warm up round before a match and they're on stage. They're just messing around. And so you have to sort of build a parser that can sort of hope to get out the overtimes, get the bathroom breaks out, those sort of things. And so first we cut down just to like the actual gameplay. And then the thing is, even in the actual gameplay, we wanted to focus on learning movement, separate from a lot of the other strategy, how to do some of the like economy management, early round exploration. And so we're actually focusing on a simpler sub-problem of just the retakes mode. So just when the bomb is planted. This sort of makes things nice in that there's always a clear objective to travel to, and you don't have to worry about longer term, like, well, what's my objective? Because navigation is sort of a different problem from should we attack bomb site A or bomb site B. And so by taking retakes, we sort of have that isolated out.
The final dataset used for training is comprised of game information that includes each player's state as a vector of information, containing their position, velocity, team ID, their status as to whether they're alive or dead, view direction, their health, and armor. It also includes the current map state, with the bomb site status and how much time is left on the clock. And then lastly, all of the events that have occurred since the last state was recorded, including the likes of gunshots, damage taken by players, and whether a particular player has died. This data is captured at a rate of 16 Hz, meaning it's recording the player data 16 times a second, or every 62 milliseconds.
So the first version of the bot was like, let's just build something state-of-the-art. So I built a fully handcrafted behavior tree that plays Counter-Strike, controls both teams, and plays Dust 2 retakes with my hand-labeled positions and like the whole and I put it on Reddit and people liked it and said it was great. They said there were a bunch of problems with it, but hey, it was a lot better than the bots that ship with Counter-Strike because, of course, they have to play on every map, and I just play retakes on one map. So I obviously solve a much simpler problem. So I wouldn't want to. It's not fair to compare them. But just say, let's build the optimal thing for one situation. And then I was like, well, what do people complain about the most? And at least on the Reddit post, the thing that they seem to complain about the most, and the thing I honed in on first, was actually the mouse model. And I spent a lot of time. I spent like 3 or 4 months actually. We did a failed SIGGRAPH submission on a mouse model. So literally, like, state of the world, predict their next mouse position. And that failed. It did. I can send you videos. It did okay when the target was standing still. It actually looked really human. It would sort of overshoot and come back and correct. But when the target was moving, it had never seen in the data examples of bad sprays because it was all looking at pros. So it never knew how to recover from its mistakes. And so the idea was we had this whole architecture. You don't want to learn everything. Learning everything from scratch in Counter-Strike seems really hard. Let's learn the components that are challenging. And so the movement model is just a node in the behavior tree. And so we can just call that, we can call it every n frames and it can run. A better version of this would have it run on a separate thread, but inspired by Unreal, where to keep things simple, the behavior tree is a single thread. We just call it. It actually takes about 7 to 8 milliseconds, about 7 milliseconds to call, but we only run it every 16 frames. So it amortizes out to less than half a millisecond. And again, a better version of this would be, let's put that actual 7 milliseconds on a separate thread so it can run across frames. We just call it one every 16 frames, and if you drop a frame, it doesn't matter. We're running in a different process.
With the data in place, the next step is to build the MLMove Bot. The model is trained in a 2-state process, first with a per-player embedding network that converts the input of each player into embedding tokens that the transformer can process. These tokens are then passed into the transformer to understand and interpret the current state of the game. This of course then helps it to predict the next outcome. Speaking of, the output of the model is broken into a probability distribution across 97 possible configurations of decisions it can make in the game, and decisions are then made by sampling from it. These options cover movement in 16 angular directions and at 3 different movement speeds, plus whether it should jump or simply stand still. Now the interesting part is that every time it does this, it also generates the output 3 times. The first for right now, at this exact time step in the game, plus it predicts what the agent should do 125 milliseconds in the future, and again for 250 milliseconds in the future, meaning it's calculating 3 actions to be taken over the space of less than half a second. The reasoning for this is that it helps prevent the model repeating actions, plus it helps it to understand the need for consistent behavior that flows towards desirable outcomes. Having built the bot, the next big question was whether or not it actually succeeded in its goals. Durst conducted a study by recording video footage from replays of 4 different types of player in matches of CSGO: regular human players, the MLMove Bot, a RuleMove Bot, which had rules for movement on a navigation mesh developed by a skilled CSGO player, and then lastly the default game bot that ships with the game. To run this, Durst then pulled in a range of evaluators with either little to no experience in Counter-Strike, alongside others who were Supreme Master First Class and Global Elite ranked players. The study was to evaluate which bots behaved the most human-like. The results scored MLMove as the most realistic bot, with written feedback suggesting it showed a lot of traits common in human play, be it trading in a skirmish to capitalise on an enemy killing their teammate, avoiding gunfights in open areas, and holding high ground and defensive positions. This didn't mean they were perfect, however, given there was still some issues with jittery movement and sometimes lacking the necessary aggression to support a teammate as they pushed forward.
What did you take away from that process? Because it seemed as if you were getting a lot of really interesting insights from them about things that they were seeing evocative of their play, but also things that maybe weren't quite the same.
I would say the first thing I was just surprised by before we got into what they did was how excited people were.
That's cool.
I would just say there are some really smart people out there who know a lot about Counter-Strike and can put together some very coherent discussions of what's good and what's bad. yeah, we saw some good examples of like trading where like, killing an enemy where the enemy's distracted. But like sometimes, like for example, the bots were way too aggressive or not aggressive enough. And so like the things they would see were like sometimes like again, like one would move in too fast and outrun his teammate. And this is sort of the thing we suspect, where you can actually inspect the attention layer. And one of the cool things about using the transformer in this manner is that you can actually inspect the transformer to see what tokens are paying attention to other tokens. And so in a language model, this means what words are related to each other. In a movement model, this actually means what does the model think, which tokens does the model think are important for the other token to govern its movement. And so you can sort of inspect who do we think is paying attention to whom in the thing via visualization. And so I would say some of the challenges may be that due to the lack of time, due to the lack of input history and the short output history, it may not be keeping a good temporal coherence. One could imagine a better attention matrix may emerge if you had more input tokens.
But outside of the player feedback, I'd argue the most critical aspect of this is that the model is so small, it could conceivably be deployed in a commercial game. In an age where generative models that are being sold both to consumers as well as the games industry often carry billions of parameters and then need to be hosted on cloud servers due to the need for gigabytes if not terabytes of memory to store them, MLMove requires 21 megabytes of memory. That's right, I said 21 megabytes. The generative model is comprised of 5.4 million parameters and was trained on a single desktop computer. With that setup, you could train a version of MLMove in around 90 minutes. When you combine this with the performance of the model, with inferencing for all players taking less than 0.5 milliseconds per game step, you have a generative AI system that can successfully generate a meaningful and practical output for use in a fast-paced first-person shooter. In theory, a game studio could build a system like MLMove, deploy it in their game, and it would have negligible effect on the technical requirements for the player to run the game. Heck, you could run it on consoles without any issue, which is all the more impressive in 2025 when most generative models could not be deployed on Xbox, PlayStation or Switch 2 without impacting available video memory and in turn visual fidelity. Coming back to your earlier point, you said specifically about wanting to build an application to show relevance and value of this, and I think that's the thing that really caught my attention really going through it, is that you want this whole thing to be able to run on the single CPU core rather than having it run on the GPU or having it run on the cloud. So I guess my original question was that always the goal, to have that feasibility of it? Or was that something that kind of evolved over time? Because the fact that you're going in with that versus, oh, we've got it running on a GPU in the cloud that's connecting to the live game, like, I think that suddenly makes it far more readily feasible as like an actual application that you would shove into the eventual end game.
I would say this is something you learn. So this is sort of one of the key surprises that we came in thinking, ML's big, ML's expensive. And this is sort of a thing you sort of hear in the gaming industry. Like modern machine learning is like ChatGPT. It's this big, huge thing, and you need like a nuclear power plant to power it. And when you start looking at these models, you realize they're solving a very general problem that's very hard. And when you start getting application specific, the problem can get much easier. And sort of the trick with a lot of these is, how can I make this as easy a problem as possible? And sort of the hard part is making the problem easy. And that then, so like, if we're just doing movement on one map, the problem becomes a lot easier. Now, sure, when we started, I thought, we'll need these huge amount of GPUs, and certain people sort of told me this wasn't going to fly. The cost structure of a modern game means that if every game, game economics would look very different if every time you connected to a first-person shooter title, you needed a GPU to back that server instance. Economics would change drastically. And so like, okay, let's see what we can do. Let's try to get the model working. And, we were just playing around with small models, or I was, because like, you start small. You don't want to start with the biggest and most complicated thing. You start with the smallest thing, and you're looking at it, and you go, wait a second, this runs really fast. And so I didn't think, it was sort of a surprise to me. I thought I would need a big GPU. I thought things would be expensive. I thought it was always, GPT, to H200s or whatever. And then you just see the run times. You're like, wait a second, like, economics may make sense here. This is actually really cool. 5.4 million parameters, 21 megs is the thing.
That's nothing.
And so no,
That's nothing.
And we didn't, and the serving is just torch script. Essentially, like PyTorch has a default like way to serve these things, call it from C++. We like there are significantly more optimized serving frameworks that you could have explored. So like I believe this is like it's sort of like this is a paper about, I would say this is not a paper, but a cool takeaway from this paper is transformers are really a good n-squared token comparison tool. Like if you look at the transformer encoder in particular, not the decoder's a little different, but the encoder, it's really, if you have n tokens and you want to learn the relationships between all n pairs of n tokens, a transformer or encoder is a highly optimized tool that industry has really made very powerful. And for a game like for a first-person shooter, or for a lot of these multiplayer titles, you do want actually n-squared analysis. You can think of the model as 10 input tokens to 10 probability distributions. And how are you going to think about 10 probability distributions simultaneously, particularly in a spatial way? And so what I found that was pretty effective was where you can sort of see how they move around, and you can see where the model's predicting their probability distributions as they move. And so you can sort of see what probability distributions you believe they may have, and then who's learning from whom. And this was just sort of I haven't worked it out yet. There's a lot more room to run here. But using these attention masks as an analysis tool, and certainly as a debugging tool, it seems to have a lot of room to run.
As we wrap up, it's worth reminding everyone that while this is an impressive application, it's not ready to ship into Counter-Strike just yet. MLMove currently is only built to handle retakes for Dust 2. In order for this to be shippable, it would need to be trained for every game mode in every map, a challenge that perhaps is attainable for an entire dev team, but not necessarily for a single PhD student. Durst, of course, has since graduated and is off in the working world, but he still has some ideas of his own of where this project could go next.
As you said, it's overfitted to one map, so there's not only just being able to train it against other maps, you've also got, as you said, like you're looking specifically at a save once a bomb's been planted.
Yes.
So you've got different contextual parts of maps of rounds running on Dust 2, but then also having other CS maps to explore. And then you've also got this kind of more broader, like what are the opportunities that then open up once you've been able to do this on multiple maps in multiple different scenarios. Like you could begin to like classify and categorize in like entire like esports teams, or like even entire like kind of subsets of like the player community, I guess. Of like, it seems like there's a huge amount of scope for this. And so, I mean, no doubt you're on one hand like happy that this is done, but also itching to come back to it in some way. Like, I guess, what are the things that you would be interested, what are the things that you would love to pursue if you had time, and what are the things that you would not love to pursue if you had time, but someone else should go and do anyway?
So I think inspecting sort of the details of the model would be a great way for someone to get started. You know, when is the attention good? When is the attention bad? When does this lead to good teamwork? When does this lead to bad teamwork? Is like, when do people like it? And how does attention impact that? It's like, and like, how do I fight with the inertia problem? I think the inertia problem is like a really hard problem that I'm sure other people, academics, have addressed better than I. And I think like that would be a problem that would be important to solve. And sort of inspecting the attention mask and visualizing that as a coaching framework would be very cool. What I am interested in, and this is sort of what we address in the end of the dissertation, I keep saying we, even though I wrote it, is...
the royal we.
Yeah, the royal we. Yeah. The King of England or something. Is essentially the way we evaluated this, separate from the user study, was looking for expert terms. Things like pushing, saving, long A, cat A, extended A. There's a rich culture of expert terms describing how people play. And these sort of terms describing how people play can be thought of as long-term plans. So I have a model that does like short-term movement. But sort of the way we think about a lot of games is that we've invented a language for each game to describe it. Thinking about what does that terminology look like, sort of going back to my programming languages background, and thinking about what does it mean to have a good language for describing behavior. And particularly then, once you have this language of behavior, well, we have these amazing long-term language models that maybe shouldn't be running in the loop, but longer-term guidance may be more economically viable. And so thinking about how do we connect these movement models to language? And then once because that was literally how we evaluated the model. So it was already good for evaluation, but I'm pretty sure it's also good for long-term guidance. And then once you have that, we're living in the age of NLP. We're living in the age of language. Why don't we take these amazing tools that are the big boy transformers and see how they might be used connected to one of these models?
Thanks for watching this episode of AI in Games all about MLMove, and a special thanks to David Durst for taking the time to chat with us. I hope you found it interesting, and you can check out more about the project via the links in the video description. Plus, head over for the written version of this episode at AIinGames.com, where you can find our weekly newsletter and help support the work we do along the way. Alright, I'm out of here. Stay safe, take care, I'll be back.